Hi everyone, this is Miriam Naime from Newcastle University and the Alan Turing Institute. Welcome to the SuperGen Smart Charging webinar series. The webinar is an activity of the Vehicle Grid Integration Group at the Alan Turing Institute. And on the webinar, we've hosted several topics related to smart charging, such as communication protocols like OCPP and ISO 15118, and also some topics on cybersecurity, such as public key infrastructure for electric vehicle ecosystem. If you're interested in those previous topics, then we have a playlist and you can check out the previous episodes on YouTube. Today, and on the note of cybersecurity, we've recently published a white paper that you can access for free. One of the other important topics related to smart charging is power quality. And today, I'm delighted to host Jan Meyer from the Technische Universität of Dresden. Jan is a senior lecturer and leader of the power quality research team there, and his interests include network disturbances and their assessment. He's a member of several national and international working groups on electromagnetic compatibility, and also he's on several technical committees such as CIRED, which is the International Conference on Electricity Distribution. Today, Jan is going to talk to us about Supraharmonics. He'll provide some backgrounds, typical sources on, and interferences, and also some talks on the measurement aspect, which I believe is not very easy, and also provide case studies on the interaction of multiple onboard chargers, which also I believe sometimes it's not so easy to understand where the source of emission is coming from, and talks a bit about fast charging. So without further delay, Jan, over to you.
Okay, thanks a lot, Miriam, for the nice introduction and the invitation to give a talk here in your seminar. Just for everybody to have a face behind the name, I have switched my camera on. I will now switch it off and start sharing my presentation. Is it visible now? No, 3. Okay.
Yes, we can see it. Thank you.
Okay, excellent. Good. So today, I would like to talk with you about the interaction and grid impact of EV charging in the frequency range 2 to 150 kilohertz. And I just want to mention that this is not for sure only my work, but also the work of many of our PhD students. Just exemplarily, I have mentioned 2 here, which have been involved in all those activities behind the scenes. So as Miriam already highlighted, I have 4 topics for today: background definitions, typical sources and interference mechanisms, the status of standardization and measurement aspects, and at the end, 2 practical case studies, which I would like to share with you for sure in 45 minutes, discussing everything until the last detail is very difficult. So from that point of view, I will make it sometimes rather brief, but we have some time at the end for discussion. So if there is any additional background knowledge that you are interested in. If we look on the present developments, for sure everybody of you is aware that we have increase in inverter-based generation, in converter-based applications like storage applications, as well as an increase in energy-efficient equipment, which is mostly driven by political policies, and they often use either active front ends or active power factor correction techniques in the novel equipment. This equipment basically is all emitting non-intentional emissions, so it is not intended to emit, but it emits due to their topologies. And what we observe is that there is a trend towards an increase of that novel intelligent equipment, which is more or less based on self-commutating topologies compared to the classical topologies, line commutating topologies that we used decades ago. Just to give you an comparison, what we talk about with regard to the waveform distortion. On the left-hand side, you can see somehow like the traditional power electronics. It's a line commutating rectifier, which we have even seen, but only one time in an electric vehicle as the onboard charging rectifier. It has a obviously non-sinusoidal waveform, as you can see here. And it has a very high total harmonic distortion, which is an index to describe the deviation from the ideal sinusoidal wave shape. On the other hand, if you look on the modern power electronics, you see that there seemed to be a more or less sinusoidal behavior, but there is such a band overlaid, which represents that higher switching frequencies of the self-commutating topologies. And therefore, for sure, there is a much higher energy efficiency at power frequency, which is usually enforced. But you basically shift the emission from the frequency range below 2 kilohertz to the frequency range above 2 kilohertz, which we would like to talk about today. Let's have a little bit of a look on the terminology. At the lower frequency distortion, so below 2 kilohertz, this is usually quite clear. We talk about integer and non-integer multiples of the power frequency. The integer multiples of the power frequency, they are usually well known as the harmonics. Yeah. The non-integer multiples, they are divided into the subharmonics, that is the distortion below the power frequency, and the interharmonics, which is basically all that distortion that is between the harmonics, and the between basically resulted in the term interharmonics. What is important is, particular for harmonics, we talk about those multiples. We do not talk about frequencies because the emission itself is linked to the power frequency itself. On the other hand, if we look on the 2 to 150 kilohertz range, the emission, which is the switching frequency and its harmonics of the devices, is normally independent of the power frequency. Which means we do not talk about multiples here. Anyway, the multiples would be rather high. We talk here about frequency, strictly speaking, frequency bands. And regarding the terminology, there is no real, let's say, terminology established yet because this phenomena is rather new. But often it is called the supraharmonics, supra coming just from a consequent continuation of the terminology below 2 kilohertz, because beyond, supra means beyond, and this is just the frequency range beyond the harmonics. Yeah, it has been introduced firstly at the past general meeting in 2013, and it is more and more common to use this term, even if it is still sometimes under discussion. But remember, if you talk about higher frequency distortion only, it's always a matter of the viewpoint, what is higher. Yeah. So if you look on subsynchronous oscillations, even 1 kilohertz is very, very high. If you talk to a guy from the EMC area, they usually say, well, that is almost DC what you talk about. Good. So how does such an emission typically looks like? In order to get a nice view on it, usually you have to high pass filter the signal in order to get rid of the power frequency and the harmonic components. And what's left over, you can exemplarily see here in the figures on the left side for an EV charger, on the right side for a computer power supply, both with different topologies. And what is quite obvious, in my opinion, is that there is a significant variation of the supraharmonic emission. It is not really constant, which makes it somehow a bit challenging to just look in the commonly used frequency domain on it. So you have certain leakage effects and so on. So just describing it in the frequency domain is usually not sufficient for the supraharmonic range. I would like to detail that a little bit on that slide. So what we usually do is if we talk about distortion, we talk about the frequency domain, yeah? So the 200 Hertz bands or the harmonics, for example. And I have shown you some time domain waveforms of the supraharmonic content, and you can see it on the left side here exemplarily for a LED lamp. Yeah, it's pretty nice. Sometimes you can see some figures in it. So this is what we usually call the blowfish. And there are even other ones. And what you can see on the left side is that there is definitely a time dependence over the power cycle, yeah, in the magnitudes. What you could expect or guess from the frequency domain is there seem to be also a frequency deviation, but that could even be just a leakage due to the magnitude variation. But only if you look in the time frequency domain, which you get, for example, if you perform a short time Fourier transform, yeah, you can see that this particular topology has a magnitude as well as a frequency deviation. Yeah, you have here up to the half, that's one power cycle roughly, and the frequency is on the y-axis, and the magnitude of the emission is represented by the color. And then you can see here that you have somehow like something like a valley here. Yeah, which is typical for this hysteresis band control, which is used in that LED lamp. So if you want a closer look on it, do not only look in the frequency domain, but also in the other domains. Particular for the troubleshooting, this is definitely beneficial. Yeah, let's come to the next point, which is about the typical sources and interference mechanisms. And the major source of non-intentional emission are, as I already briefly mentioned at the first slide, those frequency converters, for example, with or without an active front end in, for example, variable speed drive applications. You have all those rectifiers with active power factor correction, which you find in many switched mode power supplies, for example, in computers nowadays. And you find them also in the EV chargers, because today we want to talk mainly about EV charging and the possible disturbances of that to the network. For sure, also all those PV inverters, they are based on PWM-based technologies, self-commutating inverters, and the converters for storage as well. There's also a major source of intentional emission, which means emission that is intentional added or emitted in that frequency range. That's the so-called narrowband power line communication, which is particular working in the Senelec band A. And there it was long time alone, and there has been no serious issues with the communication. It's used, for example, for meter reading. But recently, when more and more devices appeared that had a non-intentional emission, then there has been also more and more challenges in the reliable power line communication. Just to give you an idea about the different frequency ranges and how that looks like in the supraharmonic range, here you see an exemplary measurement from a PV installation with a narrowband power line communication operating. And what is very typical in that frequency range is that usually the larger the size of a device, the lower is the switching frequency. So here we had about 9 large 100 kilowatt inverters. They usually, or they had switching frequencies at 3, 6, and 9 kilohertz, for example. We had a bunch of small inverters below 10 kilohertz. They usually have switching frequencies in the range 15 to 20 kilohertz, because it should be in a range where it is not audible, as they are usually, when it comes to rooftop PV, in the house. And the narrowband power line communication, you can see exemplarily here in the range between, let's say, 35 kilohertz and 90 kilohertz. It's an 8-channel system. You can count the hills. It's exactly 8 channels. What also distinguishes this frequency range a little bit from the classical harmonic range is how the units are reported. Normally, we are used to percentage values for the voltages, amps, milliamp values for the currents. And in that frequency range, which is mainly originating from CISPRE, the so-called dB microvolts or dB microamps is used. So that's maybe a little bit confusing when you hear it the first time. But just to give you an idea, what it means is that 100 dB microvolts means 100 millivolts, 100 dB microamps, 100 milliamps respectively. And if we talk in this case about 100 dB microvolts, we talk roughly about 0.04% if we assume a 230 volt nominal voltage. And 20 dB is usually 1 decade, so 120 dB microvolts is 1 volt, for example. So just to have that in mind, it's a little bit of a side aspect of the evaluation. We did a few years ago some measurements in our lab characterizing the supraharmonic emission of EVs that are commonly in the German market. So we measured 19 EVs with onboard chargers. This is only onboard chargers. And 12 of them, depending on their circuit topology, had an identifiable switching frequency. And this, let's say, first emission band, so the switching frequency itself, emission is shown here exemplarily in this figure. As you can see, is as it is usually the case, if you know one, you definitely do not know them all. They have, let's say, very different switching frequencies as well as magnitudes. Yeah, many of them are in the frequency range below 20 kilohertz, so 10 kilohertz, 15, 17, and you have to be aware that this is somehow like hearable. Yeah. But you can also find some at 80 kilohertz, even up to 100 kilohertz. Yeah. If you are interested in some of those measurements, they are available in a database that we host in Dresden, Equipment Harmonic Database, for, let's say, further research. Okay, let's talk a little bit about interferences, interference path. What can happen in that frequency range? Why do we have to deal with it? And we have to distinguish at first those devices that are intended for communication, narrowband power line communication on the left side, intentional emission. And we have those devices without communication. And for those devices without communication, we can distinguish between those devices that have a non-intentional emission and those ones that do not have a non-intentional emission. Because regarding the interferences, this doesn't matter. So an device without non-intentional emission can also be disturbed by a device with non-intentional emission. And all those interactions between those devices without communication, which is the focus today, they are called here as interference path D. And this interference path includes obvious malfunctions that can happen, restarting something or in non-intentional switching on and off. It's usually rather funny what happens in that frequency range in terms of the interferences. What we definitely can see is acoustic disturbances, so annoyable noise, particular with EV chargers. This is for one type very serious issue. And what you can also observe is additional thermal stress. That's more like a hidden interference. It's not so obvious to the user like the other ones, but it also matters. Other malfunctions, for example, is also light flickering, which had been already observed as an interference in that frequency range. Just to give you a brief idea about the thermal stress issue, here you can find the results of some measurements that we did in the laboratory with different types of lamps. So a few compact fluorescent lamps, but mostly LED lamps, and we supplied them with a voltage, including a supraharmonic part, basically according to the standard 61000-4-19, which defines the immunity levels. And as you can see, compared to the sinusoidal case in steady state conditions, you can see quite significant increase in temperature. Not for all of the lamps, just for some. So LED 57, for example, has a quite significant increase, while LED 4 is almost not affected at all. This is all depending on the topology and also the heating mechanism. And if you, for example, have such a significant increase in temperature, and you can basically observe a quite significant lifetime reduction. Another quite common interference mechanism is that acoustic noise generation. And one of the examples I already briefly mentioned, it's that, let's say, whistling noise for one particular EV. It's a Renault Zoe. And it was a pretty funny thing. So we wanted to measure here in this experiment the superposition of the different EVs, not even, I think, in the supraharmonic range, but in the harmonic range. And we switched them on one after each other. And after the second or third, the guys in the offices started to close their windows because probably they have been annoyed by that noise. Another very interesting issue which came also up in recent times is this so-called chirping noise or beating. This mainly happens if you have multiple devices of the same make, which have virtually the same switching frequency, but due to the manufacturing tolerances, they will not be exactly the same. So imagine you have 10 kilohertz and 10,001 hertz, yeah? Basically, due to the difference, you can get a beating of 1 hertz. And this is what has been, for example, observed in the interaction of two UPS systems, which is shown on the left side. So you can really see that there is sometimes no noisy emission at all. Yeah, here, so no high frequency emission. And then 2 seconds later, it is there again, it disappears, appears, disappears. This is this beating, which can then result in such a chirping noise. So that's also a quite interesting new phenomenon. Good. Let's maybe talk briefly about the standardization. So we need the standardization because of managing those interferences and still maintaining the reliable operation of the grid without too many of them. And the general concept to ensure this is the electromagnetic compatibility. And electromagnetic compatibility has two aspects. It has that one aspect of satisfactory functionality in a given electromagnetic environment. That's the so-called immunity aspect. And a device should not introduce intolerable disturbances into that environment. This is the emission aspect. And emission and immunity have to be coordinated. And this is usually done based on a so-called reference level, which is the compatibility level. And then the emission has to be adequately limited below the compatibility level in order to ensure that if the network is fully utilized, the compatibility levels are met in most of the time. We basically talk about the 95%. On the other side, the immunity has to be higher than the compatibility levels in order to ensure the disturbance-free operation. And one of the challenges in the 2 to 150 kilohertz range is now that we have also this power line communication, which requires a certain signal-to-noise ratio, which means we have to introduce a pair of compatibility levels. One, to coordinate the emission of the non-intentional emitting devices, one dose of the intentional emitting devices. Here, just a brief overview about the status quo of standardization at the moment. So normally, the compatibility level should be introduced at first. This was not really the case for the 2 to 150 kilohertz range. Here, the immunity test levels for differential mode disturbances 61000-4-19 has been introduced as the first one. Afterwards, the compatibility levels have been finally published in 2018, but after a very long and hard and also political discussion. That was very difficult to get an agreement between the manufacturers of those devices non-intentional emitting and those that want to protect the power line communication in that frequency range. Emission limits, they are in the responsibility from 9 kilohertz on by CISPRE. They are basically already established for induction cookers and lighting, and now there is also activities for the development of emission limits for other devices. So strictly the under development, what you only see here for the 2 to 9 has also to be extended to the 9 to 150 kilohertz range. Well, and if you have limits, then you basically also have to measure them reproducible and comparable. And that's the next challenge that we face. For the frequency range 2 to 150 kilohertz, strictly no normative method exists for grid measurements. There is only a normative method, the CISPRE 16, for the measurement of the equipment emission in the lab. But for the 2 to 9, we have only a 61000-47 with the informative annex. And for the 9 to 150, it's even more challenging. I will give you a little bit more detail about that on this slide, showing that framework for measuring conducted non-intentional emission. And as I said, there is a laboratory measurement method according to the CISPRE 16, but this is usually used just for measuring the equipment emission in the lab. The compatibility levels the utilities usually want also to measure the disturbance levels in the grid in order to compare it with those compatibility levels. And therefore, they usually use a grid measurement method, which is defined in the standard IEC 61000-4-30. But for 30 in its actual third edition, current third edition, has only an informative annex suggesting 3 different methods. Well, that's not really a nice situation, because there is now a considerable lack of comparability between the instruments, because some manufacturers have already started to implement it because there is a need from the utility side, but also from other stakeholders to perform such measurements, yeah, and not only in the lab for the emission of an individual piece of equipment. And we also have to think about that in the future, the 250 kilohertz range might also be included in the EN50-160, which is not an EMC standard, but more the standard which defines the quality of the product electricity that has to be provided by the network operator to the customer. But this is I would say even more important always for the utilities, yeah, because this is when they get complaints, they usually measure first according to 5160 if the product quality that they deliver meets that requirements. And if that is extended, there's also the need for such a measurement method. Just to give you an idea of how different they are, here is a comparison of the 3 methods that are provided in 61000-4-30. And particular for this emission that is not the narrowband emission, here in this frequency, you can see significant differences between the methods. Yeah. If you have a, let's say, rather small emission, then usually they provide similar results, but you should definitely be careful if you carry out such measurements to double check what's the method that has been implemented by the manufacturer in order not to compare apples and pears, particularly if there is a second instrument installed which might use a different method. So this brings me to the last part for today, the case studies. I would like to discuss with you 2 case studies. One is the interaction in a central slow charging infrastructure, so onboard chargers, and another one, a very interesting resonance amplification due to a fast charging station, both in low voltage networks. Let's have a look about the setup of that first experiment. You can see here such a slow charging central infrastructure which has been built by a network operator in Germany, Rheinfelden, close to the Swiss border, because they had I don't know, somehow like a policy from the government in their city. We would like to have EVs, and they ordered a lot of them, all the same type. It's a Renault Zoe, as it can be easily seen. And so that was a great opportunity for us to do a little bit of research there. And those EVs, they are all of the same make, same type, and a switching frequency, as I told you already, is at 10, around about 10 kilohertz. They all are 3-phase chargers at 32 amps. So they even support multiple charging modes, but that was the one that we used for this experiment. And on the right side, you can see a little bit of a little layout of the situation. So we have a medium voltage network in the upper part. Then we have the medium to low voltage transformer. If I remember right, it was a 630 kVA transformer with 4% short circuit voltage. Then we have a dedicated feeder to a junction box. I think it was about 50 meters somehow. And at the junction box, there have been 4 charging stations with 2 charging points, each connected. And we installed several measurement devices, all capable to measure the frequency range up to 150 kilohertz in the 4 different charging stations. Unfortunately, we haven't been able to measure each individual charging point, and at the begin and the end of the feeding cable. And now I will show you a few of the results of that measurements. So what we did is we only looked on the 10, or we will only look on that 10 kilohertz band. And we extend the band a little bit in order to cover the emission of all the EVs together, which means we talk about a band of 10 kilohertz plus minus 1 kilohertz. And what we can see now is the magnitude of that band depending on the number of charging cars. So remember, green is the sum. I go back a slide here. Green is the sum, which is flowing towards the network. And red is the charging station 1. Blue is the charging station 2. No cars connected, no emission at 10 kilohertz, just to ensure that there is not any other device emitting in the same frequency range. If we connect one car, we see that the emission is more or less similar. There's a slight difference, which can be, for example, caused by measurement uncertainty, but it's more or less the same. And what is probably now, or what you should look on is we talk about 1.6 amps. Yeah, we don't talk about milliamps or something like that. 1.6 amps at 10 kilohertz that are flowing into the network just because of one EV has been connected. However, it will become even more interesting if we look on the connection of the second EV. Then you can see that there is a very high current, about 4 amps flowing to charging station 1 as well as charging station 2, but not so much anymore to the network. And the more cars I connect, the lower will be the current that is flowing into the network. And this is basically due to the interaction of the different impedances. The impedance situations in the frequency range are very different compared to those that we usually expect in the harmonic range, assuming we do not have a resonance. Yeah, there we usually say that the network impedance is much lower than the impedance of the individual devices connected. So you can roughly even say it's somehow like a constant current source. In the frequency range above 2 kilohertz, this basically holds not anymore true, because the impedance situation is qualitatively completely different. Normally in that frequency range, the network impedance is higher than the input impedance of the different devices. And now, just using that simple figure, imagine we have our first car. It is that is indicated with A1, for example, and the source current A1. And you have the second one not yet connected. The only path for the current is then towards via the network. Yeah, but as soon as I connect the second car, just because of this low impedance, yeah, the first car will be much more happy to short circuit via this impedance compared to the network, which means there will be the complete impedance situation changed for the car, which means there's a higher current flowing and most of the current is flowing through the other car. So you usually have an interaction. And this was also normally the saying that most of the supraharmonic emission stays in the same installation. That this does not always hold true, we will see in the second example. What is also important, if you do a measurement of the current, for example, of that particular EV, like here indicated, then this is composed, strictly speaking, by a part that is caused by the EV itself. That's also called a primary emission, and also a part that's coming from the other EV, which is called the secondary emission. Strictly, there can even be a secondary emission from the background if there is a voltage already emission available from the network side, yeah, which makes it virtually impossible to decompose them. Yeah, you can maybe switch off one of the cars and then you can see what is the emission of that one car. But the problem is that you immediately, with switching on and off another car, you change also the impedance situation, which makes it even more difficult because then the current of one device will change again. Another interesting aspect here is this so-called beating effect, because we have multiple cars with almost the same switching frequency. And if we connect one of the EVs, you can see here on the left side the current that we have calculated now based on a cycle-by-cycle analysis at around 1.8 amps. And if we switch back to that slide, it's somehow like what we observe here. Yeah, that's that 1.8 amps. As soon as you connect the second EV, you can observe that the cycle-by-cycle value of that 10 kilohertz band will basically vary, and shows a cycle of, let's say, from here, from 0 to here, maximum to maximum, of about 2 seconds, which in turn tells us that the switching frequency of the EV2 and the EV1 deviate from each other by 0.5 hertz, manufacturing tolerances. Now, if we look on the RMS, we are, let's say, a little bit below 1 amp, yeah, which is exactly what we can see here. That's an RMS. But the momentary value can be much higher. In the ideal case, twice and nothing, completely cancelled. And well, this gets even more complex if you connect the third car, and gets increasingly chaotic with more than one. However, the effect of that variation will reduce with the number of cars. Last but not least, for this example, we looked on the propagation in the network. Remember, we did a parallel GPS synchronized measurement of the current at the beginning and the end of the feeding cable. And we just have been curious if, for example, due to the cable capacitance, there is somehow like a damping of the current, but that cannot be confirmed, at least for the 50 meters of cable in this installation. Exactly the same current that we have injected at the end reached also the bus bar of the transformer. For sure, the voltage will be lower because you get somehow like yeah, you have different devices connected which serve then as a back path for the emission. Which brings us to the second case study. And this is about a real interference that has been reported to us by a network operator, and he finally asked us if we can have a closer look on it, because it was very curious for him and honestly speaking also for us. Let's have a look on the situation. You can see here a transformer station, medium to low voltage, where 630 kVA transformer is transforming medium to the low voltage network. We have next to it here some slow charging points, where similar like those that I have explained in the example before. Then there is about a 60 meter, I think 62 meters of cable to a little junction box here at that point. And here there are is a fast charging station connected. So downstream of the transformer station, a fast charger. And the utility got a complaint of a customer about audible noise. There was an annoying noise, and probably because of that, it's a multi-family house, apartment building, and here is probably the sleeping room somehow, something like that. And so the network operator had to measure. And what was pretty curious, first of all, this noise only appeared if a particular EV has been connected here at the slow charging points. And the second is, in that case, we had 0.6 volts of at 10 kilohertz. So you probably now guess what type of EV has been connected. It was again a Renault Zoe, was here 0.6 volts, but here at the junction box about 2.3 volts at 10 kilohertz, definitely caused by that EV, so amplification of almost 4. What is really funny is that the compatibility levels that have been recently published has not been exceeded. So in order to investigate that phenomenon a little bit more, we did a set of propagation measurements. So how do we did it? We took an injection device which was able to sweep the frequency range to 250 kilohertz and injecting current. We connected it one time at the transformer station and did synchronized measurements of the voltages and the currents at the junction box as well as the transformer station. Then we switched the injection device to the junction box, injecting here, and then basically looking also on voltages and currents at the two measurement points, transformer station and junction box. And let's have first a look on the upstream propagation. So we have the injection at the junction box where the fast charger is connected. We just did a single phase injection, but that doesn't matter that much. For the 3-phase injection, you would even get a different way of coupling between the phases, but at least the phenomena is somehow like similar. So what we can see now is that's the transfer ratio. So that is basically voltage measured at the transformer station divided by voltage at the junction box. And you get a quite efficient damping, yeah, which is what we usually expect, that supraharmonic emission doesn't travel that far, which we can absolutely confirm for the upstream case. What is somehow like interesting is now the downstream case. So if we connect our injection device at the transformer station and observe the voltages at the transformer station and the junction box, dividing the junction box voltage by the transformer station voltage, then in case there is nothing connected at the junction box, we would expect this transfer ratio should be 1. It's the black one. That's true. It's 1. So theory is confirmed. Nothing unwanted seemed to be connected. The fast charging station had basically 2 more operating states in addition to disconnected or off. That's a standby stage and a charging stage. And in the standby or the idle, with the red crosses here, we could indeed see, if it is just connected, yeah, in idle mode, that there is a significant resonance amplification at 10 kilohertz and again at 20 kilohertz. So, and just because of the Renault Zoe has a 10 kilohertz switching frequency, this basically is the series resonance amplification that we observe. If it would had a switching frequency of 15 kilohertz, basically nothing had been happened. Nobody had seen that phenomenon. Yeah. As soon as the charger, the fast charger is charging, then again, the propagation characteristic or the transfer ratio changes, the frequency dependent one, which is just because of the different impedance situations. So we basically could model this behavior by a very simple circuit. Just some inductances of the line, so the capacitance of the line for the 60 meters did not have an impact at least up to 10 kilohertz. What was important was the model of the charger. Yeah, the charger model is most important with regard to its input impedance in order to do a proper simulation. Yeah, as well as this, let's say, coupling here between the phases. And what we basically could achieve is at least a pretty good match up to the first resonance. And even, let's say, the second, we can more or less see, but it's a little bit deviating from the 20 kilohertz. Yeah. So which means there is a clear proof that there is such downstream series resonance amplification possible. And this is something that is not really well let's say, taken care in the activities of determining the emission limits in that frequency range. So I guess this is something that will become a more frequent observation in the future. Okay, that brings me to the conclusion. So this was only one interference case that I presented to you. There are still much more, and as I said, some of them are even funny. Yeah. So, for example, we observed in a hairdresser's saloon that the dryers, they basically unintentionally switched on and off 30 times a day. Yeah, so that was somehow like a little bit funny for us, but definitely not for the hairdresser's lady. Yeah. Then what we also have that induction cookers generate a whistling noise. There was also a nice German paper on that. So please help me. My cooker is singing. And we also had the issue of energy meters that did not measure accurate anymore in presence of supraharmonic emission. And even this, let's say, interaction between multiple EVs of different make. Yeah, so for example, one EV starts charging, another one comes, is connected, and the first one trips. There are even more background information about those interference cases and many more in 3 study reports that have been published by Senelec SC, former SC205A. Its main signaling subcommittee. So if you are interested, I would recommend to have a look into that. And there are still a lot of open questions. So what are really adequate emission limits, especially in the focus of that possible downstream amplifications? Because, you know, usually the rather large charging infrastructures will probably not be connected at the end of a feeder, but at the transformer station. Measurements, there is a quite nice project, Supra EMI, which assists working group 9 at SC77A to develop a normative method for grid measurements. There's also a lot of discussion and debates, sometimes even also a little bit political. And for sure, the modeling of emission itself, of the propagation, needs much more further research. Yeah, that brings me to an end of my presentation. Thanks a lot for all of you to join. And those are a few impressions from our, let's say, activities here. And I'm happy now to receive your questions.
Many thanks, Jan. And I encourage the participants to leave the questions in the chat box or raise their hands if they'd like to speak. To start with some questions, have you tested other than the Renault Zoe?
Yes, we had plenty of different makes in our lab, and as I have shown you on that one slide, the different emissions, they differ a lot between them. Some are higher, some are lower, some are higher frequencies, some have lower frequencies. Yeah, so we tested more, but usually the Zoe makes the trouble.
Okay, have you contacted Zoe? Do you know to mention this to them?
Well, they are pretty well aware of that issues, at least with the first and second charger generation. As far as I know, they work on a third generation charger now, and but usually they are pretty, how you say that, disclosed. So they are not so cooperative in that. They sometimes just provide a new firmware, and then it seems to resolve the issue, but it's indeed somehow a little bit of a challenge, let's say it that way.
So what would be the best practices to the cars, to the charging manufacturers to do so that would reduce these Supraharmonics emissions?
Yeah, well, you know, they should stick with the emission limits if they are published. Let's just hope that the EMC framework is then an adequate one, really avoiding those interferences. Yeah, and anyhow, just taking a little bit aware of impedance. Yeah, so at the moment we only talk about the standardization or the emission limits in terms of current or voltage, for example, yeah, according to CISPRE. But in my opinion, in the future, particularly with that modern equipment, we might also think about requirements on the input impedance characteristic, especially in order to avoid such unwanted resonance conditions. But this is usually what is very difficult to discuss with the manufacturers.
We've got an interesting question here about, so maybe you're aware of the ISO 15118 front-end protocol between the car and the charger that uses PLC. So Thomas is wondering, there could be issues when there are hundreds of EVs trying to charge the same parking lot using PLC. Have you considered this? Do you have anything to add on this?
So I'm not so involved in the communication. So the question is if this goes via the power line. If this is the case, then I think that PLC can be affected similar to the narrowband PLC for meter reading. But I do not know too much about the protocols used and how it works, so that I can say something reliable about that. Sorry.
On the PLC note, you mentioned that during standardization, there's a bit of tension between PLC and the non-intentional emitting devices. Are you able to add a bit on how come that happened and how it was how did they find a compromise?
Oh, that's how much time do we have, Mary? No, just joking. Yeah. Well, basically at the beginning, there was the 50065 standard, which defined pretty well the emission limits for the intentional power line communication levels in the Senelec bands A, B, C, D up to, I think it's 148.5 kilohertz. And they also had a requirement on the so-called spurious emission, which is the maximum non-intentional emission that is tolerable in order to ensure the respective signal-to-noise ratio. And that spurious emission has been so low that it was not feasibly to be fulfilled by any of the manufacturers. And then they started to say, why the hell do you need to use the power line for communication? Take a different communication media. So we need it for our emission of the let's say, active front ends, for example. And then they basically try to negotiate to at least sharing there's a quasi sharing of the frequency range. So up to 30 kilohertz, there is more non-intentional emission allowed, and then there is a little bit of a drop in order to still keep some margin for the power line communication above 30 kilohertz. But still, it's difficult, and the compromise what you talk about is somehow like just political. It's very difficult to find really physical technical reasons behind it. And what is important about power line communication interference is really not only the emission itself, which can reduce the signal to noise ratio. It is also that impedance characteristic. If you basically have a very low impedance in that frequency range, which what we know, for example, from some of the PV inverters, you basically just short circuit the power line communication signal, and then you also get a quasi decrease of the signal to noise ratio. And this is much more severe or more frequent than just the disturbance by a particular emission.
Thank you. We've got some questions on immunity. So how do you achieve that? Could the harmonics be compensated using active front ends on the inverters and doing harmonic compensation?
There are some discussions and activities on that, but usually at the frequencies higher than the harmonic range, you talk about passive techniques. So a passive filter can for sure efficiently reduce it, but for sure such a passive filter will also change the impedance situation in the network, which also has to be taken care. And that's also that, let's say, scenario that the manufacturers sometimes try to, how to say, or they want to scare and say, if you require us to have such low emission, we have to install a lot of filters that you probably also do not want in your network. And indeed, they are partly true. The more capacitance we get into the network, shunt capacitance due to the filters, the more it will even affect the harmonic range. So from that point of view, so active filtering, so which means really an active filter for such high frequencies, honestly, I haven't heard about, but that does not mean that it not exists. But I think the passive filtering is at the moment the cheaper and the more efficient way.
Have you done any studies on both EV and PV and the interaction between them?
Yes, we did also some of those studies in our lab, because we had, you see it here on the slide, if you can still see the slides left lower photo. So we have now you cannot see the PV inverters. Basically here at the wall, there are PV inverters, and outside there is the EV charging, and then at that switching board, we can basically also combine them. So with regard to the interaction, you have all the typical interactions that you know between any two devices emitting supraharmonics. So you have basically, you can find, depending on the impedance ratio, the emission of the one device also in the other one. And the effect will then be additional thermal stress. If it is too high, it can even result in unwanted malfunction. But I cannot say that we have seen any very specific phenomena between EV and PV. But we did not look, let's say, with a major focus on it. We just looked on, what is the emission when they are operated together. Also, by the way, in this first case study that I presented today, there was a PV installed, but it had a switching frequency of 16 kilohertz. So then that's why it hasn't been seen in the analysis.
There are a couple of questions left, but I'm aware we're over time. Are you okay to stay a couple of more minutes?
Sure, absolutely, no problem. If you want to stay, as long as I'm not alone, then that's fine.
Excellent. So if you can look at the questions, there is one from Eddie, and I don't understand the question, so I'm going to leave it to you to check it out, if that's okay.
Yeah, I guess you refer with the K rating to the overrating in terms of additional distortion. And normally that is done for the harmonic range, because harmonics can even be higher than the supraharmonics in terms of their absolute magnitude. I'm not aware if there is any, let's say, discussion about increasing the K rating of the transformers even for the supraharmonic range. So, but I think there is still a lot of research that has to be done with regard to the real impact. Yeah. If that is the same like in the harmonics, if there is maybe some other aspects like that coupling capacitances or so that might become more important in that range. I hope I understood the question right.
If Ed, if you wanted to add something, please do so. Meanwhile, here we go. Typically, K4 or K13 is presently being specified.
Yeah, I'm not familiar with that particular ones. I guess that are somehow like different K values in the standard.
I want to check about propagation, which you mentioned. Have you?
Okay, down there. Yeah. So sorry, I saw now his response. Okay.
Okay. Would you like to add anything on that, or should I move on to propagation?
Yeah, no, you can move on. As I said, this K values is not so my field of expertise.
You've mentioned propagation, and I want to check if you have noticed or if you've studied propagation up to the MV level.
Well, we started to look on that. So what we did a few years ago is we measured the transfer characteristic of a typical MV-LV transformer in our lab, and there we could see, let's say, similar behavior. There is a pretty efficient damping. But at some frequencies, you can even have a little amplification, but it mainly depends on the impedance situations. The real measurement at the medium voltage side would require to have respective sensors, yeah, that are able to measure accurately in the 2 to 150 kilohertz range. And the classical instrument transformers that are used, so the resin casted ones, for example, they are usually not capable to measure those frequencies. So you have to set up an individual, let's say, measurement setup. And this is a little bit difficult. I know that I think Luleå University, they also did some measurements, and also Ilmenau in Germany, they also did some measurements, but we are currently doing something like that with a network operator, but it usually requires, especially in that specific times nowadays, a lot of time.
Yeah, a couple of more questions. Have you checked, or are you planning to do testing with vehicle-to-grid chargers? Or do you, we've got a project in the UK that mentioned that V2G chargers might actually be cleaning up some of the harmonics.
Yeah, okay. So we do not plan something like that, but it's probably a good idea to do so. But I can imagine that such a vehicle to grid charger is nothing else. You basically have nothing else than a converter. Yeah. So you need it as a rectifier as well as an inverter. And now the question is the topology. And for sure, all those modern equipment, they could also serve for mitigation purposes. Yeah, you just have to overrate it a little bit for that. But we have to somehow like distinguish between what they can do. So usually they might maybe filter harmonics, as you say, but probably not so much in the supraharmonic range. And for harmonics, well, there was a very interesting discussion some years ago here in Germany in a working group of the network operators, how they see this service of harmonic filtering by PV inverters owned by customers. And despite that is probably technical quite good solution, there are some legal aspects in it, yeah? Because in this case, the network operator who is responsible to deliver a respective product quality for electricity, he relies on the customer, yeah, that he filters his grid. So this is somehow a little bit of delicate and difficult situation. So from that point of view, in my opinion, as long as everybody sticks with the rules, there will probably not so much additional filtering be required, because we have to be clear that we do not try to achieve a sinusoidal voltage. That doesn't make sense. Yeah, we just have to maintain the disturbances below the compatibility levels. Yeah.
Back to equipment, are you able to briefly mention what equipment do you need to measure the emissions? How easily is for other projects to get access to those equipments? How much these equipment cost?
Well, the equipment so normally you can use each network analyzer or recorder that is capable to, or that has that respective sampling rate. So we usually use one mega sample. There was also a question in the chat I have seen about the 150 to 500 kilohertz range. Yeah, strictly speaking, you have to extend it to the 500 kilohertz. Then you might need maybe, I don't know, 10 mega samples, 5 mega samples for that. So if you have something like that, you can work with it. The only challenge is if you want to put it in the grid, you might also check with the network operator about security or safety aspects. Yeah, so we usually use something from Devitron, but it's for sure not linked to that, and it's probably a little bit more expensive than a classical power quality meter. So I cannot say you now clear values on that, but maybe in the future, if we have a normative method, then it will even be affordable for normal network operator. Yeah.
From recent presentations that I attended at ELA, they mentioned that it's important to measure voltage and current, but it's not so easy to measure the current. I wanted to check if that's still the case.
Well, yeah, so I fully agree that measuring the current is somehow, particular if you do troubleshooting, essential, in my opinion. And there is some equipment in the market that is only capable to measure voltages because of the issue of sensor accuracy. But there are also quite a lot of, or a number, let's say, a number of measurement instruments available that have. So we use, for example, voltage inputs, and we then can connect easily Rogowski coils, which have an accurate frequency response up to 500 kilohertz, for example. But you have to take care of the whole measurement chain. So you have to look what are suitable coils, how to connect it, and so on. Yeah, but it's possible. So we do it with the one that you see in the upper left. That's basically example of our measurement system.
How many years do you expect before we see regulations introduced on this?
It depends on what you mean with regulation. So luckily we have immunity and compatibility levels, emission limits. They are on the way now. There is a joint working group between SC77A, working group 1, and CISPRE-EDGE, because you know, there is, how to say that, the legal border or a limitation of responsibility. So SC77A at ISC is responsible for the frequency range up to 9 kilohertz, and CISPRE from 9 kilohertz on. The 9 kilohertz have, they seem to be arbitrary, but if you think about the interested frequency ranges, so SC77A was usually interested in the harmonics, 2.5, 3 kilohertz, while CISPRE started to be interested from 150 kilohertz because they are, let's say, protecting radio communication from interferences. Yeah, and if you logarithmically scale between 2 and 150 kilohertz, the middle is at 9. That's why they decided the 9 kilohertz. And now they have, but the physics at 8 and 15 kilohertz is for sure not really different. Yeah, and now they have to make a joint force in order to establish those emission limits. Yeah, so they are on the way. I would expect at least the draft until end of the year. The 2 to 9 kilohertz is also on the way for the emission limits, even if there are still some, let's say, issues to discuss. So I think we will have a quite, yeah, maybe, I don't know. It's always difficult to guess with standardization. End of next year, maybe. Okay. We can have something, yeah. And normative measurement methods, we truly hope to have also something in the next year, particular for the grid measurements.
Thank you. Okay, so I'd like to thank you so much for all the information you provided. I also like to thank Paul Wright at NPL who put us in touch. Before we end, is there anything you'd like to add? Where can people find more about your work?
Oh, well, we usually have a lot of publications. So otherwise, just get in touch with me. Yeah. So I think you cannot see the email address, but I can send you even the presentation if you want as a PDF, and you can distribute it amongst the participants.
And we'll also make the video of this presentation available on YouTube. So we actually can't see your email on the slide, but that's okay. As you say, we can make it available.
Yeah, no problem. Thanks a lot.
Thank you. Bye.
Okay, then thanks a lot. Bye-bye. Ciao.